All right, I wanted to do a little coding video, and I found this nice little book called Ray Tracing in One Weekend that's free online, and they show you how to build a simple ray tracer in C++. But even though it's simple, it looks pretty nice. In fact, just to kind of spoil the ending, if you follow all the steps, you get to make this image with some metal spheres and glass spheres, and looks very nice. Um, again, the book uses C++, but I'm going to use Rust because it's more fun and I really like Rust, and I think it's a fun way to learn Rust. I did this with another book called Crafting Interpreters, where that book walks you through how to write an interpreter in Java, and as I was going through it, I translated it into Rust. Um, I think you learn what the book is teaching a little better when you're not just copying the exact code they use, but having to understand it well enough to translate it. And then, of course, you're learning Rust a little bit as well if you um, wanted to learn Rust, as many people do these days. Um, all right, so let's jump in. The first thing we do is just output a simple PPM image, and PPM is a nice simple format where if you were to open the image file in a text editor, it just looks like this. It's some numbers. Um, P3 just tells the operating system or whatever is reading the file that it's a PPM file, and then the next two numbers are the width and height in pixels. The next line is the um, the range for the colors. So 255 means the value for red will vary between 0 to 255, same for green, same for blue. And so we can just print out some numbers and we have an image. So let's start. First, I'm just going to make a little script actually to run this. I just find this a little bit easier. And as you can see, this program we're going to write is just printing to standard out. So rather than having to deal with file names and stuff, I'm just going to let it print to standard out and then redirect that into a file and then open the file to look at it. Great. So first we have our image width and image height. And then we print the header, just the initial information at the top. I think it's clearer to put each line of the output as its own line. Width first and then height, and then 255. Okay, and then we're going to do a loop inside a loop. So we're looping over the height first, which means we're going row by row, and then within each row we're going pixel by pixel. All right, we're going to convert I and j to doubles, which in Rust are called F64s, and then divide by image width minus 1, which also has to be converted to F64. So our red value is 0 for the first I, meaning the left side of the image, and then as I increases, it moves up to 1. And similarly for green, going from the top, it's going to be no green to the bottom, all green. And blue is just 0. Then we need the same values but converted to integers by multiplying them by 256, or actually just slightly less than 256 to make sure we don't hit 256 exactly. They use IR here. I'm actually just going to reuse the same variable R since Rust lets you do that. So we have 255 times, or excuse me, 255.999 times R. And since we only have to go up to 255, really we can use U8 here. Oops. All right, and then same for G and B. And then finally, we just have to print this out. R, G, whoops, B. And there you go. We have an image that is reddest on the right and less red on the left, greenest on the bottom and less green on the top, and that means the lower right is the combination green plus red, which is yellow. And if you scroll down a little bit, this is what the author says it's supposed to look like. Looks like we got it right. And then you can add a little progress indicator. So since we're printing the image data to standard out, the logging has to go to standard error. So we'll use ePrintLine, or actually, excuse me, ePrint, because we want to reuse the same line. That's what the little \r is for. Scan lines remaining with the space after so that it fully erases it. Image height minus j. There we go. And then at the very end of the loop, oops, done. And then a bunch of spaces just to fully cover the previous logging. So in this case, it runs almost instantaneously. You can't really see the logging, but it'll get slower as it gets more complicated. So that is the end of chapter 2. Let's ignore the output image and go ahead and commit. Great. Okay, so next up is we're dealing with 3D vectors, right? 3D space. So we need a type that represents a 3D vector, basically a triple of floats, or actually triple of doubles they use here. And they walk you through how to use all of this stuff, or how to create this, how to multiply a vector, how to add a vector, how to divide a vector by a number, and so on, dot product, cross product, all that stuff you maybe kind of remember from high school calculus, right? I'm going to actually skip all this just because it's a little bit tedious to kind of go through and just implement all the math. And I'm going to use a pre-built library called GLAM. The only reason I'm using this one in particular is because I've been working on Bevy as well a little bit, the game engine that's written in Rust, and the vec3s that you use in a Bevy game are actually coming from GLAM, so I'm already a little familiar with them. So with the cargo add GLAM, you can see it added it here. And we'll bring in our vec3 type from there, except if you look, the GLAM vec3 type is actually 3 F32s, and we want F64s. So we're going to use dvec3. But I want to call it vec3 just because in the code in the book they call it vec3. So it might be a little confusing. We're using the type that GLAM calls dvec3, but in our code it's going to be called vec3. And the other thing they do in the book is they use the same vec3 type for colors, where the x, y, z mean the red, green, blue, points, and vectors. And they set up aliases, so I'll go ahead and do that, just like they're doing here. type color equals vec3. So color is just an alias for vec3. We could make it a separate type, but it is kind of convenient to just use the same type. And so now we have this right color function. In the book, they put this in a separate header. I'm not going to bother with that. I'm just going to keep it all in the same place. But the point of this is that it's going to take in the color as a actual color type, meaning a vec3, and print it out in the ppm format. I'm not going to have it take in the OStream. I'm just going to have it always write to standard out. So it's just going to take pixel color as a reference to a color. And I think I can actually destructure pixelcolor.x, pixelcolor.y, pixelcolor.z. Yeah, great. And then I'll say let RGB again. So these are new variables with the same name. 255.999 times R as U8. G and B, and then make them into a tuple as well. And then just copy this. Okay, great. And then here, instead of repeating all that logic, I can say let pixel color equal color new RGB, and then right color pixel color. So color new is just an alias for vec3 new, so it just takes the XYZ, which we're interpreting as RGB. All right, and then we should still get the same image because we didn't actually change anything. We just kind of refactored and brought in this other library. So once we give it a second to compile, there it is. All right.